All right, amazing. Well, hello everybody. My name is Joelle, and I'm an undergraduate at McGill University. First, I'd like to begin by thanking the organizing committee for giving me the opportunity to present my work here today. And the goal of this project, as the title implies, is to use joint kinetic Karhunen-Loève effect and 21 centimeter global signal measurements in order to improve constraints of the ionization history. The motivation behind combining these two specific signals is that they are complementary probes of reionization, with the global signal being more sensitive to the rapidly evolving modes of the ionization history, and the kSZ more sensitive to the smooth modes. Currently, we have very little data constraining the evolution of neutral hydrogen over time, and one of the many factors contributing to the difficulty of this measurement is the fact that the systematics for a lot of the proposed probes are pretty complicated to characterize and remove. And so the main results that I'm going to share with you today are that working in an appropriate basis allows us to confirm our intuition about the complementary relation between the kSZ and the global signal, and that we can work in this basis to test for the presence of systematics in data. First, I'm going to give a brief overview of the global signal and the kSZ. The global signal is the spatially averaged 21 centimeter brightness temperature, and this plot shows a theoretical prediction of what the global signal might look like as a function of time. For the global signal approximates to this expression, where the xh1 is the fraction of neutral hydrogen. And so from this expression, we can see that the global signal very closely tracks the ionization history. The kSZ effect comes from low energy CMB photons scattering off of electrons that have some bulk velocity relative to the CMB rest frame. And the kSZ is affected by reionization because reionization produces energetic electrons that contribute to the effect. The dependence of the kSZ on the ionization history is really non-trivial, but we can predict with simulations how different reionization models affect the amplitude and the shape of the kSZ power spectrum. Here are the results, for example, of a simulation showing how the midpoint of reionization can change the kSZ profile. And so although the kSZ isn't as direct a tracer of the ionization history as the global signal, we can still recover information of reionization from measurement of the kSZ power spectrum. And now, as I had mentioned before, the kSZ and the global signal are complementary probes of the ionization history. So the global signal will be more sensitive to the rapidly evolving modes of reionization. And this is because the spectra of foregrounds are smooth, as this picture from the Planck collaboration shows. And the global signal will also be relatively smooth since it tracks the average evolution of hydrogen throughout time. And so the sharply changing components will be easier to extract from the smooth foreground contaminants. The kSZ, on the other hand, is going to be more sensitive to the extended modes of reionization since it's an integrated quantity. And it turns out that if we take our measurements and cast them into an appropriate basis, we can confirm this intuition, firstly. And a basis that can highlight the complementarity between these two probes is defined by the Karhunen-Loève transform, or I'll call it the KL transfect, to two covariance matrices. And its eigenvalues effectively describe the ratio of two signals. And an example application that is probably very familiar to a lot of you of the KL transform is signal-to-noise analysis. So in this case, the eigenvalues of the KL transform would represent the signal-to-noise ratio. And people often use this method in data reduction in order to figure out which modes to keep. In this case, you would keep the modes that correspond to the highest signal-to-noise. In this project, on the other hand, we're going to perform the KL transform on simulated kSZ and 21 centimeter covariances. And we're going to get the kSZ to 21 centimeter modes and eigenvalues. And an important thing to note is that, like with any linear transformation, we can reconstruct the ionization history by taking a linear combination of the KL modes with some amplitudes, weighing them. So now I'm going to show you what we found that the KL eigenvalues and eigenmodes look like for the kSZ to 21 centimeter transformation. So here we have the eigenvalues plotted with eigenvalue number on the x-axis, and the y-axis corresponds to the kSZ to 21 centimeter information, or the eigenvalue of the transformation. And so the eigenvalues appear on the left correspond to the highest kSZ to 21 centimeter ratio, and so their corresponding modes are going to be the ones that are best measured by the kSZ. On the other end of the spectrum, we have the eigenvalues whose corresponding modes are best measured by the global signal. So they have the highest 21 centimeter information. And so we can this is the one that has the highest kSZ information, the one that's best measured by the kSZ. And we can see that it's quite smooth, and so are the next few ones that are well measured by the kSZ. The modes that are best measured by the global signal, on the other hand, are a lot more rapidly changing. And we can see a really nice result because it agrees really wonderfully with the intuition that motivated this project in the first place, that the kSZ should be sensitive to the extended modes of reionization, but this transform is more useful than just confirming our intuition. We can also use it to do statistics. And the next thing is to, now that we have this eigenvalue spectrum, we want to see if there are any modes that are well measured by both signals, and we will call these overlap modes. And here I've plotted an example of what one of these might look like. So it's not as smooth as the modes that are best measured by the kSZ, and it's not as wiggly as the ones that are best measured by the global signal. It's a bit something in between. So if we have some of these overlap modes, then given independent measurements by the two probes, we can use the overlap modes to perform some consistency checks and to make sure that there are no systematics in our data. And so we can do this with a statistical tool called the null buster test. And this test essentially answers the question, how well can we detect the presence of systematics in our data? And here's the equation for the null buster statistics. And here, nu tells us within how many sigma we can detect systematics in our data. So here Z would be a measurement of the ionization history made by the kSZ minus a measurement made by the global signal. S is a vector that essentially tells the test the shape of the systematic that you're looking for, and sigma is the noise covariance. So to get a little bit of intuition behind how this test works, you can think about an extreme scenario where we just have a perfect measurement from both probes. And then we would measure the exact same ionization history from the kSZ and the global signal, and Z would just be 0. And in real life, things rarely work out this way, so we definitely expect to have some discrepancies between the two measurements, leading to Z being non-zero. Where the null buster test becomes useful is that it can help us figure out how much of this discrepancy is due to systematics in the data rather than just pure noise. So we have So we have performed this test for a couple of statistics that what one might expect in a global signal experiment, like cable reflections. So in the figure on the left, in the vertical axis, we have the number of sigma to which we can expect to detect the cable reflection systematics. And on the bottom, we have the amplitude of the residual cable reflections, so after subtraction. So we did this test for a range of potential leftover cable reflections, and it turned out that the test can detect them to around 4 sigma for about 30 millikelvin. There is another common systematic, which is foreground contamination, and the test is even better, which it can detect foreground residuals to within order 100 sigma for. And right now what we're doing is that we're testing for some common kSZ systematics, and we've started with some residual CMB primary power, and the test is really very, very good. But this is not surprising since the kSZ primary power is so much larger. The CMB primary power is so much larger than the K. So right now we are looking into other systematics that are more comparable to the kSZ, like TSZ CIB cross spectra. And yeah, that is basically it. Just to summarize and to outline a bit of what's coming next. The KL basis, it highlights this complementary relation between the kSZ and 21 centimeter global signal. And also by working this basis, we can perform some statistical tests on modes that are well measured by both probes in order to detect whether or not there are systematics in the data. And one thing that I do want to mention that I didn't mention before is that in this project, we're setting up a general framework for using the KL transform. You're not necessarily limited if you want to apply the KL transform to the kSZ and the global signal. It can really be generalized to any other two probes that you might think of. And yeah, what we're going to be doing next, as I mentioned before, is exploring some more systematics to test and see how well this method can detect them in data. And we're also going to be looking into incorporating other probes, such as the optical depth. And that's it. Thank you for listening.